All right, so there's one more type of problem. Well, I shouldn't say one more type. Another type of problem that you might encounter for normal distribution problems might be something like this. We'll say the heights of men follow a normal distribution with mean equal to 70 and standard deviation equal to 2.9. Now, we could also write this in shorthand. There's a shorthand way of writing it, and we would just write height, and there's this squiggle, and we'd write capital N for normal distribution, and we write 70 comma 2.9. This is a shorthand way of writing, of saying the exact same thing. So instead of having to write it has a mean of this and standard deviation equal to this, we can also write it just like this. Okay? And we could ask a question, you know, what is the probability that a random male or a random man has a height we can say something like between, we'll say 69 and 72. 69 and 72 inches tall. Okay? And so for this, we would put the number 70 right here in the middle. This is our picture. And I'm going to draw a line at 72. And I'm going to draw a line at 69. And what I want to know is I want to know this area in between. Okay? And the way I'm going to solve this is to get this area what we're going to do is I'm going to take the area, all the area to the left of 72, and then I'm going to subtract off the area to the left of 69. Okay? So we're going to find this area, so this blue area, this minus this. Okay? So if I take the blue area minus the green area, what I'll be left with is this, whatever color you call this, teal. Alright? So we'll be left with this. Okay? So if so we're gonna find area to the left of 72, and we're gonna subtract minus area to the left of 69, okay? And this will equal the area between 69 and 72. Does that make sense to everyone visually? Okay? So sometimes you might get a question that says, you know, what's the probability that some measurement or whatever it is between two numbers? Well, you just do it the same as before. You find the z-score for 72, and I think we already did this one. 72 minus 70 divided by 2.9, we got 0.69, and we found the area to the left of 0.69 was 0.7549. Okay? And then we're going to find the area to the left of 69. And we're going to say 69 minus 70 divided by 2.9. So I get negative 1 divided by, whoops. Negative 1 divided by 2.9. I get negative 0.34. So the area to the left of negative 0.34 is 0.3669. Okay, so here I have 0.7549, and over here I've got 0.3669. Okay, so the area over here is going to be 0.7549 minus 0.3669. And that leaves me something else. 0.7549 minus 0.3669. And I get 0.388. And that's going to be my answer. What is the probability that a random man has a height between 69 and 72? 0.388. So the key here is you find two different numbers, find the area to the left of them, and you take the difference between those. Some of you guys are still writing, so I'll wait before I flip the page. Okay, I'm going to go ahead and flip. All right, and we have something called the inverse reading, okay? And so sometimes we are given a percentile or a proportion. Percentile or maybe proportion or percentage. Okay, and we are asked to find the corresponding measurement. So, for example, we can say, cholesterol levels have a mean of 200 and standard deviation of 30. Okay, or we can just write shorthand, we can write cholesterol comes from a normal distribution with mean 200 and standard deviation 30, okay? And we could say, what is the cholesterol level of someone in the, we'll say, 80th percentile. Okay, what does it mean to be in the 80th percentile? Does that mean your cholesterol level is higher than most people, or lower than most people? Cholesterol level is someone in the 80th percentile. Okay, so 80th percentile means that 80% of other people have cholesterol levels lower than you. Okay. %80 of other people Okay, and so when we draw our diagram here, okay, in the center I'm going to put 200, And what I'm going to do is I'm going to draw kind of a line right here. And I'm going to say that the shaded area is 80%. Okay, so this shaded area is 80%. And I want to know, what is the number here? What is the cholesterol number that goes with 80%? Does that make sense? Okay, so to get this, we first want to find the z-score that gives us 80%. Okay, so first, find the z that gives 80%. Okay, so notice we want the z that gives us 80%, not the, we're not looking up z equal to 0.8. We want the z that gives us 80%, okay? And so we have to go to the table, and we're going to go through all of the numbers for the area. And we want the one that's closest to 80%. And the one that I find that's closest to 80% is 0.7995. Okay? Because I have 0.7995 and 0.8023. 0.7995 is closer to 80%. Okay? So what is the z that gives me 0.7995? Z is equal to 0.84. Okay? So closest value to 80% is 0.7995. The z that gives that, the corresponding z, is 0.84. Okay? So here I have a z that's equal to 0.84. How can I go from a z back to the measurement? Okay? Well, here I'm going to just use the z formula and say z is x minus mu divided by sigma. I'm going to plug in the values I know. I know that my z is 0.84. This is equal to the unknown x minus, what's my mu? 200. And what's my sigma? 30. Okay? So at this point it's just algebra. And if I solve for x, so because I'm running out of space, I'm going to just go straight to the answer. I'm going to say x is equal to 200 plus 0.84 times 30. So let's do that. So we do 200 plus 0.84 times 30, and I get 225.2. Okay, so what is the cholesterol of someone in the 80th percentile? That person's cholesterol is 225.2. So in this case, we first found the z-score that gives me 80%, or the thing closest to 80%. And then once we have the z-score, we convert the z-score into a cholesterol level. Okay. All right. So let's try another one of these out. I'll give you guys an example to work through. Just make sure that we got a good grasp on this. Okay. So we'll say. All right. So I'll just say heights of. We'll say heights of women come from a normal distribution. I'm going to say 64 and standard deviation 2.8. And I'll say, how tall is a woman in the 15th percentile for height? So go ahead and try that out. See what happens. Let's take a look. So we want how tall is a woman in the 15th percentile? Bless you. So let's, we're going to draw a line right here, and we want 15%. Okay, so we're going to look up the value in the table closest to 15%, and the number we find is 0.1492, right? I think that's the number that we find that's closest to 15%. We find 0.1492, and I think a lot of you guys got this far in the table. Okay, so we find 0.1492, and when we look at that, we see 0.1492 is in the row negative 1.0 and the column 0.04. Okay, so when you bring these together, you have to be careful. Okay, the corresponding z here is going to be negative 1.04, and I think a lot of you guys wrote down z is equal to negative 1.4. Okay, this is not correct, because if we looked up z equal to negative 1.4, that's this number, 0.0808. Okay, we want negative 1.04, which gives me 0.1492. Okay, so just be careful there. Okay, so we find that the corresponding z here is equal to negative 1.04, right? And we want to convert this back into a height. So we say z is equal to x minus mu divided by sigma. So I got negative 1.04 is equal to x minus the mu of 64 divided by 2.8. So I multiply both sides by 2.8. I got 2.8 times negative 1.04 is equal to x minus 64. I add 64 to both sides. So I have 64 plus 2.8 times negative 1.04 is equal to x. And from that, I get x 64 plus 2.8 times negative 1.04. And this gives me 61.088. So how tall is a woman in the 15th percentile for height? If we want to be really precise, we would say 61.088, but probably for most people, just say 61 inches. That's probably good enough. Okay? Is that good with everybody? All right, so you can expect to see both, these normal model type of problems to appear on the midterm exam, and I have posted some practice problems on the course webpage. Okay, so the other table I passed out today says binomial probabilities. Okay, so let's talk about the binomial distribution and using the binomial probability table. Okay. All right, so I have to preface this and say when we cover the binomial probabilities, this is like binomial light. Okay, so if you were to take another statistics class, they might cover the binomial distribution in greater detail with some more formulas. We're not going to bother with that. We're going to just use this probability table. But other things do exist. So let's take a look. The binomial distribution applies to situations where you repeat the same random activity several times. Okay, and every time you repeat it, you're either only two things are possible. Something happens, or the outcome is a particular thing, or it's not. Okay, and we are interested in getting a particular number of what we call quote-unquote successes. Okay, so a simple example and I'll write all of this down. Simple example of a binomial situation is flipping a coin, say 6 times. Okay, I'm going to flip a coin 6 times. Every time I flip the coin, so I'm basically repeating the same random trial 6 times. Every time I flip the coin, I have a 50% chance of the coin landing heads. Okay, and whenever I flip the coin, I only have 2 possible outcomes. The coin either lands heads or it doesn't. Okay, and with the coin, it's going to be heads or tails. And we could ask, what's the probability that I get 4 heads out of 6 flips? Okay, or what's the probability that the coin lands heads 3 times out of 6? That's a binomial situation. Another binomial situation is, let's say, a basketball player takes a bunch of free throws, right? Okay, maybe the basketball player takes 8 free throws in a game. Okay, and if it's a good basketball player, maybe he has a 90% chance of making the free throw. Okay, so we'll say he's a 90% shooter. So, if the player takes 8 free throws in a game, there's only 2 possible outcomes. The ball goes in the net or it does not. Okay, and in that case, success is an appropriate use of the word. And we can say, okay, probability of a success for any shot is 90%. If the person takes eight shots, what's the probability he gets 6 or 7 or something like that? Okay, these are binomial situations where you're repeating the same thing multiple times. Every time you do it, you have 2 possible outcomes. That's where the binomial part comes in. And then and we want to know what's the probability of getting a certain number of successes. Okay, so we'll say binomial situations. Situations include repeating the same random trial we'll say n times. Okay, each trial has 2 outcomes. And in the literature, these outcomes have come to be known as success and failure. Okay, but they, in everyday language, we associate success with good things and failure with bad things. But these are just arbitrary labels, okay? We can call getting the coin landing heads as a success and getting tails as a failure. We could have just as equally called tails success and heads failure, okay? We can be talking about, patients having... us detecting some kind of disease in a patient, okay? And if we detect the disease, that might be arbitrarily labeled a success, even though, in all accounts, it's not probably a good thing. So, the labels of success and failure are just arbitrary, okay? But that's just what they're called in the literature, okay? Each trial has a probability of P, probability of success P. Okay. Each trial is independent of other trials. What does it mean to be independent? Is not affected by the other trials, right? Every time you flip a coin, it's not affected by the other coin flips. Now, as far as the basketball player goes, perhaps subsequent shots are affected by previous performance. Maybe, maybe not. If we wanted to apply the binomial distribution, we're going to have to say we're going to assume that every shot is independent. That might not be a safe assumption. Okay? Maybe it is, maybe it's not. Okay? Each trial is independent of other trials. Okay? And we are interested in getting X successes. Okay. Once I show you how to use the binomial table and do binomial distributions, you're going to realize that it's very easy. The hardest part is recognizing when we have a binomial situation, okay? And sometimes we mix up binomial situations with probability situations, okay? So, today you took a quiz on, probability things, and we said, you're going to play a game 3 times or something like that, okay? Sometimes they sound very similar to binomial situations. The key difference, okay, is that in binomial situations or in binomial problems, the order of outcomes does not matter, okay? In binomial problems, the order of outcomes does not matter. Okay. We are simply interested in a particular number of successes. Okay, so I'll let you guys get this written down, and I'll flip the slide, and then I'll show you an example that's binomial and an example that is not. Okay, so we'll say a basketball player consistently makes 90% of his free throws. Okay, so he takes, we'll say, 4 free throws in a game. What is the probability he makes 3 out of the 4 shots? Okay, and I should say he makes exactly 3. Okay, so this is a binomial problem, okay? Because here, the order that he makes those 3 shots does not matter, okay? So this is a binomial problem. The order does not matter. Okay, we would be happy if he makes the first 3 shots and misses the last shot, or we would be happy if he misses the first shot but makes the last 3. Either of those situations are fine, or any other arrangement is fine. Okay, so any arrangement of 4 shots where he makes 3 of them So any arrangement of 4 shots where he makes 3 of them satisfies the question of making 3 out of 4 shots. Okay. Does that make sense? Okay. And so in this problem, to answer, we identify N, X, and P. Okay? So what is our n? It's how many trials we do. So the number of how many trials total. Okay, so n is how many trials, and that is 4. He's going to take 4 shots. X is the number of trials, or number of successes we want. I'm sorry, not trials. Number of successes we want. And so what's that? Yeah, we want 3 successes. Number of successes desired. So this is 3. And P is the probability of success in each trial. And that is 0.9, right? Okay, so we have n, x, and p. And so to answer this, we go to our table. And let me find the binomial table here. Okay, so oops. We go to n equal to 4. Okay, and inside n equal to 4, we come over here and we go to x equal to 3. Okay, so I have n 4, x 3, and then I slide over into the column p equal to 0.9. Okay, and so my answer there is 0.292. We see that? 0.292. Okay, and so my answer, so we look up n is 4, x is 3, and p is 0.9. So my answer is 0.292. What's the probability that he makes 3 out of the 4 shots? 0.292. Okay, that's simple enough, right? Okay, so we can have a similar sounding problem, and I'm just going to change. So we're going to say, we start off the same here, okay? But instead of asking what's the probability he makes exactly 3 out of the 4 shots, so I've got a basketball player consistently makes 90% of his 3 throws. He takes 4 free throws in a game. We're going to say, what is the probability he makes the first 3 shots and misses the last one? So this one is not binomial because the order matters. Okay, what is the order of things that that has to happen? It has to go make, miss, right? And so the probabilities will be 0.9 times 0.9 times 0.9 times 0.1. So this one becomes just a regular old probability problem, like the kinds you saw on today's quiz. So you do 0.9 times 0.9 times 0.9 times 0.1, whoops, and you get 0.0729. This is okay? All right, so let me try giving you one more example thing. So we'll say you buy a trick coin. Okay, where it says the coin will land heads with probability 0.7. you flip the coin uh, 9 times. And we're going to say, what is the probability it lands heads 7, 8, or 9 times. So we'll say 7 or more times. Okay. So is this a binomial problem? It is, because the order doesn't matter. We just want to get 7 or more heads. Okay, so we're going to try to identify n, x, and p. What is our n? How many trials do we have total? We're going to flip it 9 times, so our n is 9. What is my x? It's going to be 7, 8, and 9. Okay, because it says 7 or more times. What's the probability that it lands heads 7 or more times? I've got x equal to 7, 8, and 9. Okay, and what's my p? 0.7. Okay, so I'm going to go to the table. We're going to go to n equal to 9, and we're going to look up x equal to 7, 8, and 9. And we're going to go to the column that has p equal to 0.7. So I see 0.267, 0.156, and 0.040. So I got x equal to 7, x equal to 8, x equal to 9, and I already forgot my numbers. I got 0.267, 0.156, and 0.040. Yeah? And then what do I do with these? We add them together, right? Because basically it's 7 or 8 or 9. And then when we have or situations, we add them together and we subtract the overlap. Is there any overlap? No, because it's not possible to have exactly 7 heads and at the same time have exactly 8 heads. Okay? So there's no overlap for us to worry about. So we just add these together. Okay? Add them together. And we get something 0.267 plus 0.156 plus 0.040, and I get 0.463. And there is our answer. So if the coin lands heads with probability 0.7 and you flip it 9 times, what's the probability that it will land heads 7 or more times? That happens with probability 0.463. Do we feel okay about this? Okay, great. Let me, I guess I'll give you some, I don't know, hints or topics to know for the midterm. So as far as the midterm, I think for the calculation-based questions, I really think studying the practice quizzes will be very helpful. So I guess topics for the conceptual questions. Okay, so all right, make sure you can identify what is a numeric variable versus what's a categorical variable. Okay, so if I say we I don't know. I can't think of an example here. You know, we record students' grades as A, B, C, or D, or F. Is that numerical or categorical? Categorical, right? If we're going to record your grade as a letter, that's going to be a categorical variable. Okay. All right. Make sure you know which graphic displays apply for numeric variables, which ones apply for categorical variables. Okay? What are the graphic displays we have for categorical variables? Bar charts, yeah. Also pie charts, but I don't like those, right? Okay. What about numeric? What do we have for numeric? Histograms, dot plots, box plots, okay. When do we use scatter plots? In linear regression, we need two numeric variables. For scatter plot, you need two numeric variables, okay? So make sure you know when you're using each thing. Okay, you should know what the numeric summaries do, okay? Not just like how to calculate them, but what they do. So, or like kind of their definitions or what their meanings are, right? So the mean is the balance point, okay? The median is the halfway point, okay? And they both measure this idea of center, where the center of your data is. Okay. What do standard deviation and IQR measure? Spread. They measure spread, okay? And we didn't really give them conceptual definitions. We just said standard deviation and IQR are ways to measure spread, right? Okay. You should know what it means for something to be left skewed versus right skewed versus symmetric. What it means to be unimodal versus bimodal, or I guess whatever. Multimodal. Okay, if we have, when is it appropriate to use linear regression? What's the key thing in order for you to use linear regression? The data has to be reasonably linear, right? Okay. And how can we tell if something is linear? We have to make a scatter plot and look at it, right? And if the problem doesn't say that it's linear, you can't assume that it's linear, right? If the problem just says correlation is 0.8, that doesn't mean it's linear. Okay. You should know the interpretations of correlation. What does it mean to have R equal to 0.9, or R equal to 1, or R equal to negative 0.4, or whatever, right? You know, positive direction, negative direction, you know, weak or strong, okay? And again, those interpretations only make sense if it's linear. So right now I'm just talking about the conceptual stuff, right? So all of you should go through your practice quizzes and make sure you can do all of the calculation-based stuff. All right, what other conceptual things should you know? Okay, know what it means for events to be mutually exclusive, and know what it means for events to be independent. Oh yes, and okay. Know the differences between observational studies and experiments. You know, all of those details. Okay. I feel like that's a pretty good list. I might have missed a couple things here and there, but I feel like that if you study that list of conceptual topics and get a good grasp on that, and if you work through the practice quizzes, you should be well prepared for the midterm. Okay, so we'll see you guys next week. Good luck as you guys study, and with that we'll just end a little early today.